All right, everyone. Good morning for some and good afternoon for others. This morning and today we're starting with Piotr Chrusciel from Vienna, who's giving the talk on hyperbolic mass and Masket gluing. Piotr, thank you very much for joining us. Please take it away.
Yes, a good morning, everyone out there. It's actually good afternoon here. So this is joint work with Erwan Delay and Rafaela Witte concerning some properties of hyperbolic mass. And these are the two theorems. One I want just to mention, and the other one I will present you some more details. So the theorem, which actually goes a few years back already, that the energy momentum vector of conformally compact n-dimensional asymptotically locally hyperbolic manifolds with spherical infinity and with scalar curvature satisfying a certain inequality is time-like future pointing or vanishes. So that's a theorem we proved a few years back. And a more recent result, which I want to present, is that there exist three-dimensional conformally compact asymptotically locally hyperbolic Riemannian manifolds with constant negative scalar curvature, which have arbitrarily high genus at infinity and which have negative total mass, right? So one theorem says that in some circumstances, the energy momentum vector is time-like future pointing, so it's a positivity theorem for energy momentum. The other one is that actually there exist manifolds which have negative mass. Here, this theorem with Erwan, the key point is this spherical infinity condition. This theorem was known since 2001 for spin manifolds by using Witten type methods. So if you assume a spin manifold, there's nothing new. And different story if topology infinity is not spherical. And obviously that's the key of my talk, that there exist solutions which have negative mass. The theorem, in fact, was that our version was that the energy momentum is time-like future pointing or light-like future pointing or vanishes. And but there's a beautiful paper by Huang, Zhang, and Martin, which shows that light-like cannot occur either. So in fact, time-like future pointing or vanishes is the right statement. Generalizes to many ends and boundaries satisfying curvature, mean curvature inequality. And this is something that Greg will be talking about in his next talk. If you might have noticed that I haven't made any restrictions on dimension in my statement. Well, if dimension is smaller than 7, then this is published. The proof is uses already well-known established results. In dimensions higher than 7, this is based on preprints by law convention and Yao. So if you when assume that the result in these preprints are correct, then our result follows in high dimensions. In low dimensions, it is certainly well established now. Well, the key idea which is shared between this theorem and the theorem that I going to talk about with on higher genius is the Maskit-gluing construction by Eisenberg, Lee, and Stavro, which goes back to some gluing constructions by Matteo and Paccard. So dimension 3 plus 1, positive at energy, spherical infinity, that's the theorem. But in 3 plus 1, if you have asymptotic, hyperbolic asymptotics, you can have various topologies in infinity. And when the topology of your conformal boundary at infinity is toroidal, then the famous Harvestmeyers metrics, which provide examples which have negative mass. So spherical infinity positivity is known. Toroidal case, there exist negative mass solutions. And the question is, well, what happens in 3 plus 1 dimensional spacetimes? Asymptotic, hyperbolic asymptotics, but higher genus topology infinity. and no black hole boundaries. And so this is exactly the theorem, right? So there exist three-dimensional manifolds, etc., with negative total mass. So here, asymptotically locally hyperbolic means that the metric approaches a hyperbolic metric at large distances. And the precise asymptotics is something which we call asymptotically Birmingham-Kotler. I'm going to describe this asymptotics in more detail. Then here, another important point is conformally compact, which means that there is no interior boundary. In our case, only a boundary at infinity. The negative mass solutions were known with a black hole boundary, and I'm going to present them. So this is the first example without a black hole boundary. Now, this condition R of G is equal to -6 in general relativity corresponds to time symmetric vacuum general relativistic initial data, and there is a freedom in normalizing the cosmological constant by rescaling, so we just normalize to -6. The main point is arbitrary height genius here, and this is three-dimensional. I don't know how to generalize this to higher dimensions. So why should we care about this at all? Well, asymptotically hyperbolic manifolds appear everywhere nowadays in theoretical physics, like in supergravities, in string theory, holography, CFT ADS. So there's a lot of work on these manifolds or related to these manifolds in physics. But if you forget about all these fancy theories that I mentioned, they in fact appear naturally as space-like hypersurfaces in the vanilla solutions of Einstein equations with or without a cosmological constant lambda. Hyperbolic space occurs as a t equals 0 slice in anti-de Sitter space-time, and but it also occurs as a hyperboloid in Minkowski space-time. And if you take a de Sitter space-time, there are actually hypersurfaces which have asymptotic, hyperbolic asymptotics, which lives in there as well. And well, if this is not enough for you, that well, that's an interesting mathematical problem. Are there bounds on the mass with or without supplementary conditions in general relativity? What do you need to impose to?
But Piotr, excuse
Yes.
me, does this counterexample apply in those cases?
Well, that's not a counterexample. I'm just saying, well, these are examples of manifolds which have negative mass, but the topology at infinity is different than the standard one, right? So that's the
this I understand.
So okay. That's not a counterexample to anything. That's an example to something, right? But you shouldn't expect mass to be positive if you have complicated topology at infinity, even without black hole boundaries.
Yes. Okay. Thanks.
You're welcome. So, so the model metrics, right? So I already mentioned them. Kotler, Birmingham. Kotler was a colleague in Vienna some 8 years ago. He was the first one to write some of these metrics, maybe not all of them, but Birmingham was the one who wrote the whole family, which is presented here. So the metric is static. There is a lapse function which is given here. HK here is a T and R independent Einstein metric on a n-1 dimensional compact manifold, right? So you have a time, you have a radius coordinate, and you have a compact n-1 dimensional manifold. Compactness is not necessary for this to be a solution of Einstein equations, but these also, but it's when you're defining mass, it's useful to have it, and I'm going to return to this later. And so there's this constant kappa here, which appears here, and it has to do with the sign of the scalar curvature of these manifolds, right? So the Einstein tensor of this metric HK is proportional to the metric, and this sign K, when you're normalizing this K is 0, 1, or -1, appears in the lapse function. M is an arbitrary number, real number. So if you want to define mass of a manifold, well, then you can talk about asymptotically Kotler-Birmingham matrix, and that's what we're going to think about. So an example would be the Cutler-Birmingham matrix. So what you do is you just there's a preferred solution in this class which has m equals 0. It's preferred because this one has various problems if r goes to 0. So in this sense, this m equals 0 gives you a preferred solution in this class. And you can just define the mass of this metric gm compared to the asymptotics as this number here, right? So that's I'm going to give you a more sophisticated definition which applies to much more general situations shortly, but in this case the mass would be actually only this parameter. If you take this metric, that's the mass. They are singular unless the slabs function has positive zeros, and if there is a positive 0 here, then this corresponds to a black hole horizon in all the standard sense of black holes. And good. So these are the Cutler-Birmingham metrics, and then, well, what about Harvestmeyers? Well, Harvestmeyers, you just first take these metrics, you assume that kappa is 0. So this factor, which was any compact metric on this under this R square, is now assumed to be Ricci flat. So it splits as a one coordinates and another Ricci flat metric. If you want to, this can be still any dimensions. And what you do is you're going to change the sign of this minus Vm square becomes Vm square. So the minus becomes a plus on this term, and the plus on the d theta square terms becomes a minus. And you can check or argue or verify that this is again a Ricci flat metric. It's still Lorentzian because now this minus has become a plus, but this plus has become a minus, and it's still asymptotic to a Horowitz, to a Birmingham-Cutler metric in the sense which I introduced before. But now, of course, the infinities will be toroidal. So if m is positive, this function has a 0, and in the Birmingham-Cutler case, the zeros were horizons, but now they were horizons because there was a minus sign here. But now we have a plus sign, and you can check that that this set where m positive, Vm vanishes, is a smooth, totally geodesic submanifold. In n dimension equals 3, you get a co-geodesic. When you choose the period of this angle appropriately. And this period has to be chosen depending upon m. So one has to be a little careful here, right? So this, if you change m, you have actually to change the period here. But if you change the period here, for R large, this theta parameter is one of your parameter on the conformal boundary at infinity. So changing m corresponds to changing the topology at infinity, or the geometry at infinity, not the topology, but the geometry, right? So one has to keep this in mind. So the metric at conformal infinity, indeed, you remove the R squares and stuff like that, you get one d theta square factor from this and one from that. So it's say a torus at infinity in dimension 3+1 or high dimensional Ricci flat manifold. But the geometry depends upon m. Now the point is that the mass now for the Birmingham-Cutler matrix, the total mass was proportional to m. Here, when you use a suitable notion of mass, and I'm going to tell you what this notion is very shortly, then you'll find that the total mass is actually arbitrarily negative proportional to the negative of m. So if you have a toroidal infinity, you can have negative mass. The positive energy theorem does not work in this setting. There's a conjecture by Horowitz and Myers that this matrix realizes minima of energy at fixed conformal structure infinity. So in other words, the mass can be arbitrarily negative. There's no lower bound of mass, but if you start changing the mass, you're changing the topology and the geometry at infinity, right? So if you fix the geometry at infinity, then this matrix will be the minima of mass. So there is a conjecture which gives you a version of the positive energy theorem. Well, in this case, the right thing to compare with is not the flat Kotler metric, but the toroidal Kotler metric, but the Harvestmeyers metric, and this should provide you the minimum of energy. Good. So how do we construct manifolds which have a negative mass and higher genus infinity? Or indeed, how do we prove that the mass is positive in the spherical case? We use something called the Maskit-gluing. Goes back to a theorem by Eisenberg, Lee, and Stavrov. You take two asymptotically hyperbolic manifolds. They have constant scalar curvature, say, or you could also formulate a similar theorem in the case where you have inequalities on the energy or in the vacuum. Then you can construct a new one by making a connected sum at the conformal boundary at infinity, right? So this is the picture. You have two metrics which have a conformal boundary at infinity, and you make a connected sum not inside, but near the boundary. So if you make a connected sum inside, you'll be gluing two spheres together. Here, actually, you're gluing two half spheres, right? So you have a half sphere which extends to the interior, and it's cut off by the boundary at infinity. And so you get this glued manifold, and that's a very nice theorem proved by Eisenberg, Lee, and Stavrov. And for our purposes, we need a slightly fancier version of this that you can localize this construction by a Carlotto-Schön type hyperbolic glowing. So I'm going to return to this shortly. So let me just mention this at this stage. And the question is whether you do it a la Eisenberg, Lee, and Stavrov, or whether you do it a la Carlotto-Schön. Then what is the energy momentum of the new initial data set? Now, this theorem already is telling you the following, that you can take, for example, a black hole which has a toroidal geometry, toroidal infinity, make a connected sum with something more complicated at infinity, a la Eisenberg, Lee, Stavrov. Then you're going to get a solution of Einstein equations, which again has a black hole and has a different topology and infinity. Right? So the topology is everything is satisfied. So, for example, you can do it with manifold with constant scalar curvature, but the topology of the boundary is not the same as the topology of infinity. This follows immediately from this construction. But the question is, can you control the mass when you do this, right? Can you say something about the mass of the new manifolds? And that's the one of the main points of this talk here. But if you want to say something about mass, you should have to know how to define mass. And there are two standard ways in the literature. One is very popular by Wald, called Noether charge, and which is exactly the same as the geometric Hamiltonian methods developed by Kijowski and Tulczyjew in 1979. So somehow people are willing to ignore Kijowski and Tulczyjew and always quote Wald, but this is exactly the same approach, and the results you get are the same. And when you use this method, you end up with various perhaps complicated expression for the energy, and let me show you one which I like and which is convenient for our purposes. So in this setup where we have a metric which approaches a Kotler-Bergenham metric with m equals 0, so this are locally asymptotic hyperbolic metrics in dimension 3+1. Well, this is actually here the dimension can be anything. Then this is the formula for the energy, which is obtained from this formula of Wald or Kijewski and Tulczyjew or many other people by 2 millions integration by parts, right? So something extremely popular in the literature in string theory or CFT ADS is something called the holographic mass. Well, this formula is actually the same as the holographic mass when both this formula and the holographic mass formula are defined. There's a non-empty intersection of space-times where this is true, but sometimes the holographic mass can be actually defined in more general settings. On one hand, on the other hand, it requires much more control of the asymptotics than this formula does. So it has some advantages. But whenever both are defined, then they give the same number. So in this formula, if you are familiar with mass formula, usually they're written in some kind of disgusting non-covariant form. This one looks actually almost covariant. Obviously, the Ricci is the Ricci tensor of the space metric, so it's an invariant object. Here is its trace. So this part is invariant. This one isn't quite invariant because you're using this function v, and this function v is defined through the asymptotic coordinates. Right? So there is some potential coordinate dependence which shows up in this formula through this formula, and then of course you can show that this does not depend upon the coordinate, the choice of this coordinate r in a natural class of coordinates. So this is geometric, but one has to keep in mind that this is not something intrinsically defined by the metric G. It is defined by the metric and the background to which it approaches. Right. So in particular, depending upon whether you're using a background with 0, plus or minus 1, you're going to take a different function here. Actually, under my asymptotics, this does not matter. Just adding the constant here does not matter, but the choice of this function r will be play an important role. Well, this actually generalizes a little because this was only the mass. Here is a formula for energy momentum, and this is a formula you can write down when you have spherical conformal on infinity, because you have then more of these important functions which are called static potentials or static kids or something like that, where infinity is spherical with a round metric at infinity. You get actually a whole family of functions that you can put here, and this defines not a number but a vector, well actually a collection of numbers, n plus 1 numbers, where n is the space dimension, and that's called total energy momentum. If you asked our colleague Sederbaum from Tübingen, she will tell you that she calls this center of mass, something like that, which is completely wrong, but I'm not going to go into this discussion. This is the energy momentum. So this you have when topology at infinity is spherical. Any other topology, so if you take a sphere and take a quotient by a subgroup, or so you get a length space, or you get a torus at infinity, or you get a higher genus, you only have one function, v, that's always this one, and you have only one expression. The spherical case is special, where you have more expressions, and the spherical case is also special because when you have a round metric at infinity as your conformal metric, you can still make a conformal isometry of this round metric, and it remains a metric, asymptotically hyperbolic and everything. And if you do this, then these p mu's transform, right? And they transform into each other. And this is a classical calculation that they transform as a Lorentz vector under isometries of the hyperbolic metric. So it's a hyperbolic metric has this says this spherical infinity. Spherical infinity, the isometries are the conformal group of the sphere, but the conformal group of the sphere is the same as the Lorentz group, and well, at least the connected components of identity. And you can check that this p mu's, these numbers, actually is going to transform as a Lorentz vectors under isometries of a hyperbolic metric. This is important for the positive energy theorem in the spherical case, but here I'm more interested in the toroidal case. So let me just tell you what is the Scalotto-Schoen type gluing. Well, this is your torus at infinity. And you just zoom on a small region here. So the green thing is the boundary of infinity, and the blue circle here is the boundary of, well, let's just think on 3+1 dimensions. So this is a two-dimensional torus. This is the boundary at infinity. You have a circle and a half sphere, which bounds a half sphere, which goes into space-time, right? So this extends into space-time. You have another half sphere, slightly smaller, which expands into space-time. And the point of the scalar type glowing is the following: you take whatever metric you had here. Well, we're interested obviously asymptotically the Birmingham-Kotler metrics. So take any one of those metrics here, then you can carve out a half sphere near infinity in this blue region with a smaller half sphere red inside, and do terrible things to your metric so that outside of this half blue half sphere, you have the metric you started with. So nothing changed outside of this half sphere. Inside this half sphere, the red one, you have exactly hyperbolic space, right? So the metric inside this half sphere is hyperbolic, outside your original one, and there's something terrible happening here in the transition region, but it's relatively terrible, but it's still you have enough control so that you can that this metric is asymptotically hyperbolic in a very precise sense, and has a well-defined, for example, energy. Well, in this case, energy, not energy momentum, because there's only one. So in particular, because the metric inside here, this half sphere is exactly hyperbolic, there's a funny property of hyperbolic geometry that half spheres in this half plane representation of the Poincaré of hyperbolic space are totally geodesic. So when you cut off the everything, so the interior of this thing from your initial torus, you're going to end up with a manifold with a topology which has which looks like that, right? So you can just think that you went carving into the inside, and if you double it across this boundary, because the boundary is totally geodesic, you get a perfectly smooth metric on your manifold. And now the new manifold has, of course, at infinity a higher genus topology. So let me just illustrate this. This is a little counterintuitive that this thing is actually totally geodesic. So if you don't, if you have no experience with that, so if we were in a case where the boundary is actually spherical, right? So what you do is then this is your boundary at infinity, and you do your Carlotto-Schön gluing so that you get inside this region a half ball, which is where the metric is exactly hyperbolic. Now, if you apply a boost or a conformal transformation at infinity, or a hyperbolic symmetry of your asymptotic hyperbolic metric, you apply this. Well, that's certainly not a symmetry of your whole metric, but it's hyperbolic isometries, are isometries of this metric in the neighborhood of this cap. Then you're going to get, you can extend this little region near the North Pole to go well beyond the equator by an isometry. So now this small region, which was a small region which was hyperbolic, becomes more than half of your manifold is actually exactly hyperbolic. So now you do the same with another copy of your manifold, except that you rotate it by upside down, right? So this picture is the same as here, and then you do the boost and rotate everything upside down, and then you can just glue things together across the equator, and you get a perfectly smooth manifold where you have double what you started with, except for this something which was a small region initially. So this works when the boundary is exactly is spherical, but everything here was happening is local near, everything important is local near this region, right? So this hopefully makes clear to you that the boundary of this half ball is actually totally geodesic, and you can glue things together in a smooth way. Now, one of the points of this construction is that once you've done all this, the energy momentum is obviously additive, right? So of course, my question was, what happens with mass when you do these Musket glowings? Well, if you've done it the way I did it here, then the energy momentum of the new manifold will be the sum of the previous ones, because this integral, if you are in this region where the metric is exactly hyperbolic, then the red part vanishes, and therefore there will be no contribution in this integral coming from the glowing region. So the whole contribution comes either from the orange one and gives you the energy momentum of the initial original one thing after you've done your boosts, or plus the energy momentum of the blue thing after you've done all your boosts. So this is what happens in the spherical case, and that's what you use to prove the spherical positive energy theorem. And that's a long story which I don't want to talk about in this talk. So what I'm interested in now is the mass formula. What happens if you have a toroidal background? I said, oh, we take one of these Birmingham-Kotler metrics at infinity, take its slice equals 0, you get a hyperbolic metric in the, well, in this case, half Poincare model representation. So you have a flat metric here. That's your metric at infinity. Theta and phi are periodic. Now you do this gluing, you get of two toroidal metrics, you get something which is a Bretzel, higher genus, so genus 2 background. And now when you're measuring the mass of this new solution, it's now with respect to the background associated with this topology. So the initial background was this flat metric, but now at infinity, you don't have a flat metric, you have a metric of converger -1, right, which you can write in coordinates like that if you want to. But so this is a new background, right? So when you're defining your total mass, the total mass is the integral of the boundary of whatever I showed you it is. And if you made your glowing symmetrically, then on each half of the glued manifold, this conformal, this negatively curved metric is actually conformal to the flat one, right? So this is just uniformization theorem. So, but in any case, take a torus removable ball, you get a metric, and you can write a negatively curved metric on this, and it's conformal to the flat one. Now, as I said before, initial mass respect to B, final man with respect to B bar. So you have to know how this radius function changes in the formula for the energy, and then, well, you just work it out. That's pretty simple. That this R bar is actually E2 minus omega half, right? So E to omega is the conformal factor which relates this negatively curved metric at infinity with the flat one, and the new radius function actually is 1 over square root of this function plus lower order terms. And of course, if you're taking these integrals to infinity, the lower order terms don't matter. Initial mass integral over the torus of the original function grad R. The new one, integral over the glued manifold of the new lapse function, which is R bar square -1, because now you have to include this -1 in the definition of the static potential. And then, but this the lower order terms don't matter. This -1 doesn't matter, but what matters is R bar has changed. So in this, so you just replace R bar by E2 minus omega half R, right? So And so this is the formula for the mass, and that's one of our main theorems of this paper, is that we have two metrics which, well, a metric G which is asymptotic to two different backgrounds. One is first Birmingham-Kotler with a coordinate R and a coefficient K. Another one, a new coordinate R bar, a new coefficient K bar. Now these two metrics are, by the uniformization to theorem, you can relate them as conformal factor one with respect to the other, and the original metric was defined using the first initial radius function. The final one is defined like that, right? So this R here gets replaced by this factor here. So in the spherical case, this is the factor which produces the boosts, and this is the factor which makes the energy become a vector. You make a conformal transformation on your sphere, you can do it globally, then this function E2, this conformal factor, is defined globally, and you get a global redefinition of your energy. And if you work out what happens, it's actually acting as a boost on your energy momentum vector. Now, the sphere case is the only one where this makes sense globally, right? Because this representation, if you have two metrics with different K and K bar, well, if they have the same K and it's not a sphere, this factor will be 1. And if they have different Ks, so K is not K bar, you won't find something like that on a compact manifold. Here there is actually a surprising geometry which I wasn't really aware of, and which will show up shortly in what we're doing, is that in fact there's something called the punctured torus. So you can put a hyperbolic metric on a torus minus a point, and then so this is called a punctured torus. You can think of this as exactly the geometry is what is said here, right? That you have a point, a puncture on this torus, and which you put a conformal factor which blows up, and then you can indeed have two asymptotic backgrounds, one being the hyperbolic one with on this punctured torus, and the original one on the torus. But of course, if you take a punctured torus, strictly speaking, it's not a compact manifold, right? So in other words, you have to be a little careful, because this conformal factor is going to blow up near this puncture. So this integral could perhaps be not convergent. In our case, it's going to converge, because near the puncture, this is 0. So near the puncture, we are in this region where we glued in exactly hyperbolic space. So near the puncture, this is 0, and then this energy is perfectly well defined. And so you can think of, even on a torus, you can put the puncture in it, think of it as being not asymptotically Kotler with toroidal infinity, but asymptotically Kotler with a punctured torus at infinity, and you have a different mass coming with this. Good. So we're doing our gluing. Let's go back to our gluing, right? So we take two tori, replace, make a Carlotto-Schön gluing. We had a exactly hyperbolic metric here, cut it down, glue together. Each half of the glued manifold, as by this calculation, acquires this mass, right? So this is the mass here. And now I want to claim that this can be made negative, and for this I need to control this integral. So on each half you get actually, it's not an integral over the whole manifold, but you remove this little disk around your puncture, right? So, and then when you do the Carlotto-Schön gluing, then of course the theorem is not that you can do it no matter what the disk at infinity is, but it has to be small. And so the theorem is that you can make your gluing when this disk is sufficiently small. So you get a whole family of gluings with disk getting smaller and smaller, but there is a threshold, and of course this threshold, you don't know what it is. So what you need to first take into account that this conformal factor, when you shrink the size of this disk where you do the glowing, will depend upon epsilon. And you have epsilon is not small, so you really need to understand what happens with this conformal factor when epsilon goes to 0. So the limit epsilon goes to 0 is needed, and then sufficiently good estimates are needed for the behavior of this conformal factor when this gluing neck shrinks to make sure that the error terms which arise when you do this construction coming from this do not affect your sign of the integral. So this is our theorem here. When you do a Musket glowing to Harvestmeyers metric, parameter m, you do it symmetrically, then this e to omega epsilon, the conformal factor coming from on each half, which makes the flat metric, transforms it to a metric with scalar curvature equal -1. On each half, it's going to tend the conformal factor of the punctured torus. Okay, so you can think of this thing as splitting. You know, the neck became longer and thinner in the middle. And when epsilon is 0, these things actually are infinitely half away, where each of these things is the punctured torus. And then the energy of each half tends to this simple formula. So this is the initial parameter m, and you get the conformal factor of the punctured torus. And entering here, this integral turns out to be finite, and in the limit, you get something which is obviously negative. And so then to finish the proof, it's just sufficient to show that the error terms which arise in your formula for the energy go to 0. Well, there's a bit of technical work to do here. So, and then the claim is that in the limit, you get something negative, and the mass actually tends to this when epsilon goes to 0. So when epsilon is sufficiently small, you're going to get a manifold which has negative mass. Now, so this is the existence of solutions of negative mass. This construction can be iterated. So for one, you can do it with several punctures rather than one. So this is an example where you made a puncture here, another puncture here, and instead of gluing it with another manifold, you glue it to itself. So same thing happens. The region connecting these punctures will get longer and longer, thinner and thinner, and in the mass, in the end, you're going to get a negative mass. You can do it on 2 manifolds with, let's see how many, I took 4 punctures on each donut, and you get this kind of topology at infinity. What's interesting is that, well, the first aim was to construct examples with negative mass, and that's what we did. But now, once you know how to do this, you can think, well, what else can I do with this? So, for example, you can lower the total mass of a asymptotically locally hyperbolic manifold by a localized deformation for geometries with very thin necks. Okay, so what's the story here? In order to control well the mass, I really needed to have very thin necks. But once I have thin and long necks at infinity, my construction can be just used to, for example, connect this neck here with a neck here. And if this manifold has positive mass, then the new one, where I connect these 2 regions together, will have lower mass than the initial one, because you can take this one to have negative mass and this one whatever it had. So you're going to lower the mass of the initial manifold, but you're going to do this, well, at infinity, of course, dramatic things happen because you're changing the topology at infinity, but in each individual manifold, nothing changes except for a small neighborhood of where you're doing your construction, because everything is localized near these punctures here. So the space-time geometry, if you want to think about it here, or this is the slice equals 0 of your initial data set, is going to be exactly the same as you had before, except for a small deformation near this glowing region. So you're lowering the total mass of the solution by adding to it something very complicated. Now in physics, when you can do things like that, the physicists will shout instabilities, right? So this thing cannot be stable. If you can lower mass, then this theory doesn't make sense. It's not stable. You can make arbitrary low mass, and dramatic things can happen. So physicists would tell you this means instabilities. Well, I think that's maybe right. That would be interesting to really see if there is some precise sense in which you can make instabilities out of this. But one could then conjecture that topologies which have geometries at infinity with very thin necks are unstables. This also tells you that there are various higher genus mass inequalities proved by Liam Neves, proved by Gibbons. There were nice results on product topology by Greg and colleagues. So there are many partial results concerning mass when you have higher genus inequalities, and these examples tell you that you can actually when you remove the condition of product topology, then you're going to lose the theorems that you had before. So the construction can be used to show that several existing theorems are sharp in this context. Now, Harvestmeyers conjectured that if you take a torus at infinity, then the Harvestmeyers, and you look at solutions which have no black hole boundary, then the Harvestmeyers solutions are absolute minima of mass, right? So it's tempting to conjecture that something similar is true for higher genus. So if you take a higher genus solution, then in each conformal class at infinity, there should be a lower bound on the mass, right? So my construction of lowering mass actually changes the geometry at infinity or the conformal class at infinity. Well, here, if you fix the conformal geometry in infinity, maybe there is a lower bound on the mass. And obviously, with these constructions, we know that this lower bound, if it exists, is negative, except if the boundary is spherical. And when you have such an inequality, of course, the minimum, if it exists, is always coming with negative metrics, with static metrics. So then the conjecture would be that there exist static metrics with higher genus infinity and negative mass and conformally compact without black hole boundaries. I don't know how to prove this, but I think it's an interesting research topic. So, well, my time isn't quite up yet, but maybe it's a good moment to stop if there are questions and stop here.
Hello, can you hear me?
Yes, I do.
Yes. I mean, you do have a few minutes left, so if you had some slides that you wanted to include, you're most welcome to. If not, then
well, I'd be glad to include those, but they're just a little off topic. So if there are questions, I'll be happy to take them. If not, I will just show these last two slides. But Let me just at least pause and see if somebody wants to ask something about dimension 3 plus 1, because the other ones are essentially a summary of what is known in higher dimensions, which becomes extremely confusing. So I think maybe it was confusing enough at this stage.
Okay,
So
let's thank Piotr, and let's. It was a beautiful talk with lots of ideas there. Are there any questions? So Lars, I think, had a hand, I believe. Yeah.
Hi, Lars.
Hi. Very nice. So this, I mean, I vaguely remember about this Harvestmeyers instanton. That, I mean, the reason you can have you can have a negative mass there is that the topology doesn't allow you to have an asymptotically killing spinner, right? And I mean, so if you think about such asymptotically hyperbolic spaces with different boundary topologies, there would be, I guess some would admit, so for topological reasons, some would admit, killing spinners or asymptotically killing spinners, and some would not.
So I have a perverse proof that you have higher genus at infinity, you cannot have asymptotic killing spinners. And the proof is, well, if you could have one, then there you wouldn't have Birmingham Kotler metrics with negative mass. So that's yeah, I don't know much about obstructions to existence of spinners, but this shows you that no way, right? Because the Witten,
yeah,
Witten
no, I just wanted to mention
work.
this because it's something that that's one aspect of this example that's very, very annoying, so to speak.
Yes, right. So exactly, and so in fact, if you have a toroidal infinity, you can have there is a topology which admits spinners. That's the one which is a product. And so and then you get a positive energy theorem for black hole solutions, or for the hyperbolic cusp. But of course, the Horowitz-Myers one has the wrong interior for
Exactly.
spinners.
Right.
Yeah. That's why the Witten proofs don't work.
Yeah.
Yes, line.
Piotr, it's a really striking examples. So I want to ask you about when you talk about the mass formula. So after you do gluing, you have a mass formula. And can you go back to last slide?
Right. This one or the previous one?
Let's see. Where you know, like one part, you know the matrix asymptotically to some geometry, and yeah, this one.
Okay.
And the other part asymptotic to the other geometry, right? So so this is just one end, right? So you saying you have a matrix, you know, is asymptotic to two backgrounds at different region. So how do you really define that? So how about the interpolating region?
Well, the definition is pure asymptotics, right?
Right.
So it's everything's happening near the conformal boundary infinity. You don't care about what's happening. I mean, the nice thing is that this part, right, is completely geometric. So you don't have to worry about it at all. You have some decay rates, which guarantee that the integral converges. And so the only thing you have to worry about is this conformal factor. And so indeed, this conformal factor is coming from the uniformization theorem, and therefore quite abstract. But in some cases, you can control it. For example, in this punctured torus case, you have quite a bit of information about this. So you can define this with respect to this punctured torus. And for our purposes, of course, we don't have an explicit formula for the conformal factor when we glue things together, but well, we have to do some analysis to show what happens when you're shrinking the epsilon, the radius where you do the gluing to 0, and that's actually probably the most interesting part of our work, and was the hardest one when we did it, but well, it's a long story in two-dimensional geometry, which will probably not interest many people. Yeah.
So I just feel I probably misunderstood the formula. So here you have after you glue, you have one part, the matrix asymptotic to B, and the other part, the matrix asymptotic to B bar. Is that right? And then now you compute the energy.
Right.
So here the integral will be on the separate region.
Exactly. So there'll be, and the point is that there is a gluing region where this is 0, right? So so you don't have to know, no matter what happens with this function, which would typically be blowing up in this gluing region, doesn't matter, right? So that's the
okay.
Yeah, that's why it works. Yeah.
All right. So if you allow me to ask another question. So I've been wondering, so you say when the you prescribe like for the toroidal conformal infinity, when you prescribe the geometry, the Harvestmeyers conjecture say their instantons is the one which has the lowest energy, right? And I wonder if there are examples which tells you actually have other examples have negative energy which is above those minimum threshold, but it's not 0. So do you have examples somehow between like continuously realize those energy?
We wrote a paper with Luc Nguyen and I think Hamed Barzegar here, where we show we give there are various classes of metrics which so if you assume some symmetries, you can prove Harvestmeyers with symmetries, and so you have a whole family of metrics which have the right asymptotics, which live on this manifold, and for which the Harvestmeyers conjecture is true. So the general case is open, but at least there are classes of metrics with symmetries which for which you can actually prove this.
So are those also, you can also give example which have the energies, which somehow the energy as a like a function on the matrix can continuously change from the negative
right
down.
Right, exactly. Right, yeah.
I see.
Yeah.
Thank you.
Yeah.
That's great.
Hi, Piotr. I just wanted to maybe follow up on that question a bit. So this omega is just determined by the geometry on the conformal boundary, right?
Right.
So you don't get like fairly good understanding of what it is then? Because it seems like.
So when we tried to understand what it is, we read a million of papers by so Volpert, Mumford. There's something called Mumford-Deligne compactification of the Teichmüller space or something like that. So there's a lot of work which is already done on what is known about. Well, here actually, this problem reduces to the following: where you're shrinking down this radius of gluing, you're actually really going to the boundary of the Teichmüller space, right? So you're taking a sequence of geometries on this bretzel, and you're going to the boundary of the Teichmüller space. And then there's something called the Deligne-Mumford compactification, which tells you abstractly that this is something. But it's not good enough to control these integrals. So we had to, we didn't find in the literature anything which would allow us from these abstract statements about Teichmüller space to control the integrals that occur here. And so we had to do it by hand. So there's some maybe interesting insight into boundary of Teichmüller space that we obtained by explicitly telling you how these things behave when you shrink the gluing radius to 0. And well, as I said, yeah, I couldn't find this in the literature about it.
So I mean, so related to in particular, the the spaces you construct for each fixed genus, you don't really have a sense of how small you can make the mass.
Or the neck, you know, can go to be arbitrarily small. I mean, the geometry is really approaching this one, right?
I'm saying when after the construction, yeah, this formula that you have, that one, the formula you have for E bar, right? You know it's negative, but you can't see how negative it is.
Oh, it can be anything, right? Because the mass parameter is arbitrary, right? So yes, so a very interesting question is, what is this integral?
Yeah, that was the yes. That
Yes.
was the follow-up.
And I know pretty poor bounds on it. So you can write down bounds. Yeah, I don't remember them offhand. Obviously, there is an arbitrary parameter m here, so that certainly can be arbitrarily negative. There's an arbitrary scaling coming from the area of your boundary. So this value of this thing can be anything, right? But given geometry at infinity and a mass, how much is this integral? That's not known. There are papers about controlling this conformal factor, which give you upper lower bound, but there's no, yeah.
But when you say
I wish I knew.
You say it can be anything. You're saying you can make the example so that that number is as small as you want, because I thought you don't know what the red.
No. So what I'm saying that this M can be anything you want,
right?
And
but
the conformal class
controls...
can be anything you want, but this is a function which is bounded between some constants, which is known to be bounded between some constants for some simple cases. In general, it's not known.
Okay, I thought that you said that the M controls the geometry of infinity, right? And then therefore it's going to affect the red factor.
So let me say it again. This factor here is the conformal factor of the punctured torus, right? And the punctured torus, there's many punctured tori because you can just take any torus and take a puncture, you can move it around. It's going to change the conformal factor. And I think there's probably an obvious bound from below, which is 1, or from above, coming from elliptic inequalities from the two-dimensional Yamabe equation. But the other one is much more complicated, right? So there's a trivial bound in one direction, and the other one is known in some very special cases. And a sharp bound on this function is actually an important problem in some in number theory, but it's not known. So.
Okay, thanks.
Okay, let's thank Piotr again for a beautiful talk and questions.